Okay, this video is on the square root and the cube root functions. I'm going to start out with the square root function. Now, we've already talked about this function, y equals x squared, which the graph looks like a parabola. And we've also already talked about how if we want to undo taking the square of something, well, in order to undo squaring something, we would have to take the square root of it. Well, turns out that the inverse of the y equals x squared function is the square root function. And we're going to see that by taking this graph and reflecting it across the line y equals x, because we know that's how we take the inverse of the graph of a function. We reflect it across the line y equals x. So let's take this graph and reflect it across this line here. And let's see, if I reflect this point's going to be over here somehow. So this part here is going to look something like that. That's that part there on the right side. And then this part, let's see, it's going to flip. Looks like it's going to flip all the way over to this quadrant. And I think looks something like this. So what we end up with, this red graph, is kind of a sideways looking parabola, and that would be the inverse of this graph. We just reflected it across the line y equals x. Well, if you take a look at this, and you'll see there in your notes it says, what problem do you notice with the reflected function? And some of you may have already noticed a problem with this. If you want to think a little bit about why there may be some problem with this function. And it turns out that the problem is in calling this shape a function, because one thing that we remember about functions is that a function can only have one y value for every x value. You can only have one output for every input. And one way that you may remember we check that is by this thing called the vertical line test. In other words, if I can draw a vertical line through the graph of my function, and if it hits the function in more than one place, well, then we say it fails the vertical line test. And that's what I mean when I say, what problem do you notice with this reflected function, is that, well, I could say the problem, I could say, well, it's not a function. And I guess more specifically I could say it's not a function because it fails the vertical line test. So, and in fact, this red graph here, it's not a function because it fails the vertical line test. We have another word that we use for graphs like this that aren't actually functions. We call them relations. But it turns out we would like to have a function, and the way we deal with the fact that this is not a function is we essentially just kind of ignore the bottom part of the graph. So in other words, the square root function, which is to say the inverse of the y equals x squared function, is just going to be the top part of this graph. So this is what our square root function looks like. It's just the top half of that sideways parabola. Now, let's talk some about the characteristics of this particular function, this particular graph. Its vertex, or if you prefer, its endpoint, is this point right here. I guess it would be the vertex if we had the whole, if we had the top and the bottom parts of that graph. So that's just the point 0, 0, the origin. The end behavior, as x gets larger and larger, that is, as x approaches, you say, as x approaches infinity, as x gets larger and larger, it turns out y also gets larger and larger. So y approaches infinity. The domain, now notice I've got some restrictions on my domain. When I look for what x values I have, I can see I've got all these positive x values. That is, my function exists here where x is positive. I also have x equal to 0, that's right here. But notice I don't have any negative x values. So my domain is just going to be x greater than or equal to 0. My range, I can see I've also got some restrictions on my range. I can see I have positive y values right here, and I can see y is equal to 0 right here, but I don't have any negative y values. So my range then is going to be y greater than or equal to 0. Asymptotes, turns out I don't have any asymptotes here because I don't have any lines, I don't have any dotted line that I could draw on here that my function keeps getting closer and closer to but never touches. My y values, they just keep getting larger and larger and larger and larger. So there aren't any asymptotes here. I'll say none. Now symmetry, this is a characteristic we haven't talked about before, or at least in the context of these functions. Symmetry just means, is there some kind of way that I can, is there like a line that I could draw that would be the mirror image, would be the reflection line. And for this particular graph, there's not. Now there was, when I still had this bottom part down here, but then that wasn't a function. That would have been, I would have had a line symmetry right there, but this one doesn't have any symmetry. So we'll just call that none for no symmetry. All right, now let's take a look at the cube root function. And again, we're going to do the same thing that we did before. This function here is the function y equals x cubed. And in order to get the cube root function, if I have x cubed, and if I take the inverse of that, then I'm going to get the cube root. And in order to take the inverse of it, graphically, once again, I'm going to reflect it over this line y equals x. So let's do that. So let's see. All right, so it looks like this top part here looks kind of like that top part of my y equals x squared when I did the y equals x squared reflection. This part, let's see, now when this gets reflected over the line y equals x, let's see. This part's going to look like that. And then, let's see. Keep reflecting these points across this line. And that's going to look something like that. So here, again in red, I've got my reflection of this y equals x cubed function, and this is my function y equals the cube root of x. And now I'm going to ask the same question that I asked before, which is, do I see any problems with this? And at least in terms of it being a function, no, there aren't any problems, because notice it passes the vertical line test. Anywhere I draw a vertical line, it's only going to hit my red graph in one place. So there aren't any problems with this one, and so I can use the whole, I can use essentially both parts of this graph. Now I want to talk about the characteristics of this function as well, the characteristics of the cube root function. The vertex, now the vertex here, also called sometimes the anchor point or just the center point, and again it's the point 0, 0. In behavior, as x approaches positive infinity, let's say, as x approaches positive infinity, I can see as x gets larger and larger, y again gets larger and larger, so it's going to approach positive infinity. Now this one I've got another in behavior in the other direction, because as x approaches negative infinity, as it goes this way, I can see my graph here gets more and more and more negative. So I'll say as x approaches negative infinity, y also approaches negative infinity. So I kind of got two ends here on my end behavior. My domain, well, let's see. For positive x values, my graph exists here for positive x values. For negative x values, it also exists. And for x equals 0, it exists. So my domain is all real numbers. I got the same thing for my range. I can see I've got positive y values. That's where my graph exists right here. I've got negative y values down here. and I've got y equals 0. So my range, y equals all real numbers. Asymptotes, again, since as x gets larger and larger, y also gets larger and larger. There's no line that it approaches but never gets close to. I don't have any asymptotes. Now, symmetry on this one. Notice that this one, when we talk about symmetry, there's not actually a line that I can draw. There's not a line that I can draw that would give a reflection that would have both sides of this, reflected across the line. There is, however, something that we call rotational symmetry. And notice if you, kind of think of putting a pin, a thumbtack or something right here in the origin and turning it 180 degrees, well, hopefully you can see that if you turn that 180 degrees, then you would get exactly the same graph. In other words, this has what we call rotational symmetry. In other words, if we rotated this 180 degrees, the graph would just rotate right back onto itself. So it has rotational symmetry, and I guess let's go ahead and say, but no line symmetry. Now, last thing we want to talk about for these two functions is the graphing form. And we've seen this before for other functions. And remember, all we're going to do when we want to put a particular function in graphing form is we want to basically add in our a and d parameters. A goes in the front multiplied, d goes on the end added. And then we want to replace the x value in our function with this b times x plus c expression. So if you want to pause the video here, you can see if you can come up with the graphing form of these two functions. And then if you want to come back after pausing and see if you get the same thing that I get. All right, so I want to put the a parameter in front. So it's going to be a times something and then plus d out here at the end. So a plus, let's see, f of b times x plus c. Well, my function is the square root, so I'm just going to put b times x plus c under my square root symbol. And this is the graphing form of my square root function. All right, let's do the same thing for the cube root function. A goes in front, a times, and I'm going to have my plus d out here on the end. A plus the cube root of, replace x with b times x plus c. And that's the graphing form of my cube root function.